So it turns out this theorem about partial fraction decomposition comes with a few caveats. And the first caveat is that if you have repeated linear factors, so in this case, this x minus 1 squared would be the repeated linear factor, then you can't treat this as though it's just 3x minus 1 over x times x plus 1. So in other words, let's just assume we were doing this problem. Well, you can already see how it factors. But according to the theorem, and again, I'm not justifying this theorem here. I'm just telling you what it says. But we'll just use it. So the distinct linear factors are x, so a over x, and then you've got a b over x plus 1. We can't stop here, so this is important. You have to add another term that's divided over the second power of that term, of that repeated linear factor. So this is, I'll put a star over this. When you have repeated linear factors, you have to include a term that involves all possible powers of that repeated linear factor. All right, so that's really the one comment. At this point, we can continue this doing what we normally do. So I would have to multiply this by x plus 1 squared. This guy times x plus 1. And this guy by x and x. And so now we can see that 3x minus 1 equals a x plus 1 squared plus bx times x plus 1 plus cx. Okay, so we'll choose some good values here. You'll notice one little caveat here, which we'll point out when it happens. But let's say when x equals -1, that's a good choice. That'll make the first two terms go away. So then you get -3 minus 1 is -4. And cx becomes a -c. So c equals 4. And the other choice might be that we plug in 0 for x. So when x is 0, notice the two right terms on the right side go away. And then you get -1 on the left side equals a. So that one was easy. So now we're actually out of choices, or out of good numbers to plug in that would make things disappear, because we've used 1, we used -1, nothing else we plug in will make things disappear. But what we're going to do is we're just going to plug in another convenient value, like 1. And we'll get on the left-hand side 3 minus 1, which is 2. On the right-hand side, we'll get 1 plus 1 is 2 squared is 4. 4a plus 2b plus c. And we are going to use the fact that we just figured out what c and a were already. So that means that 2 equals 4 times -1 plus 2b plus 4. And now we'll solve for b. So the right-hand side actually becomes just 2 equals 2b. Sorry, just double-checking that math. So that means that b is 1. And now we can say that this function here can be expressed as our a, which is -1, over x, plus our b, which was 1, over x plus 1, plus our c, which is 4, over x plus 1 squared. Alright, and so now I would break this up. I'm going to break this up into these two pieces. So this is easy. This next piece is actually easy too. Actually, I'll do it all at once. What I want to recommend this 4 over x plus 1 squared, write that as 4 times x plus 1 to the negative 2. And the reason I'm saying that is because you actually don't need to use any special technique to evaluate or to find the antiderivative of that guy. You just need to undo the power rule. So that's kind of the trick, what can be somewhat confusing when you're dealing with all these integrals and you don't know what to do. You're in the partial fraction mode, so you look at this 4 over x plus 1 squared and think you need to do something fancy, but actually, if you just rewrite it as 4 times x plus 1 to the negative 2, it's going to be really easy and straightforward to do. So this final answer would be negative ln absolute value of x plus ln absolute value of x plus 1. And then this guy here, we're going to have to add 1 to the exponent, so it should be x plus 1 to the negative 1. And then we're going to have to undo the fact that that positive 4 is going to be positive, so I'm going to need to put a negative 4 to make that happen. And so that's our final answer, except we need to add the plus c. And we're done. Now again, last comment that I've already made in a prior video, but if you take multiple choice tests, just note that this can be expressed as, by property of logs, ln of it can be written like that. Okay, so absolute value is the division because that's a minus in front, and when you subtract logs, it's the same as dividing within one log, and then you can write, and then the absolute value of a quotient is the quotient of the absolute value. So I'm just using that property. So you might see an answer, you could see an answer choice that looks more like that. But if you're writing the answer down for your teacher, it shouldn't, hopefully they don't take off for not using those properties.